the propaganda I gave for the class the first day was we want to do calculus. So we want to understand functions and linear approximations. And so what we're up to at this point is, okay, we've got vectors set up. Now we want to talk about, well, what kinds of linear functions are there? So leading into the calculus, we want linear functions that will give best linear approximations of a differentiable function. So to do this then, we need to talk about what linear functions are. So some of you have seen this in some form, most of you have not. I'm not assuming any prior knowledge, so yell at me if what I'm saying doesn't make sense. So, first of all, you guys need to learn some notation. You haven't seen this before, but if you want to talk about a function, what does it do? Just in general terms, what's a function?
Input, output.
Input and output. So, if you input things that live in X, and you output things that live in Y, mathematicians' notation for a function is this notation. A function f maps, or is a function from the set X, which is called what? The inputs for a function. Domain. And the outputs, it maps things in the domain to the
codomain.
So some people are taught codomain.
Range.
Most people call it range. But there is not uniform agreement on this. So a kind of picture that you will see as you proceed in your math lives is you have a function that takes things in X and maps them to Y. So a point in here that's called little x will get sent over to a point f of x that lives in Y. And we aren't going to discuss it today, but it will come up later. Do you remember the words one-to-one and onto? What does one-to-one mean?
Every input there's only one output.
No, that's what a function is.
For every x.
Right, yeah.
So one-to-one means no two x's go to the same y.
Right.
Right.
And onto means?
Every part of the range is used.
So the set of all the values of f fills up all of y. So there's no points in y that are not of the form f of x. Don't you love double negatives? Every point of y is f of x for some x. Yes, sir?
If y is the range, what word do you use for the green area there?
Aha! Just fell right in my trap. That's written f capital X, and that's called the image of f. So the points that get hit are called the image. And onto is saying every point gets hit, so every point is an image. All right, so in the setting of linear algebra, we're going to be studying functions from Rn to Rm that are compatible with all this vector stuff we've been doing for the last week. So it's called a linear transformation or a linear map. I will usually say one or the other of those. So you take vectors with n components, you feed them into this machine, and out pops a vector with m components. All right, so what are our vector operations that we've been doing for vector addition? So you could talk about adding two vectors. Maybe I'll use different letters. I'll write V and W here for now. So you know how to add vectors. What might you guess would be a good formula to have. T of V plus T of W. So that's sort of compatible with addition, that you can add the vectors first, apply T, and it's the same as first applying T and then adding the vectors. And what's our other vector operation? Scalar multiplication. We want to do T of CV, and that should be
C
T of V. All right, so this is reminding you of our definition of subspace, where we had to check closure under addition and scalar multiplication. This is T behaves properly with respect to those same structures. So that's what a linear map is. Oh yeah, so before I erase this, Math Club is having their opening event. You're all invited tonight at 5 p.m. Lots of food and drinks and various games.
It's in the matrix.
It's in the Matrix, which is room 308 around the corner. So everyone's invited. Okie dokie. Examples. What in the world would be an example of a linear map? So let's start off with the simplest possible thing you could ever do. I'll call it example 0. Can you give me a linear function from R to R?
F of x equals x.
Okay. So T of real number x is x. Does that work?
Yeah.
If you put in x plus y here, you get x plus y, so that works. If you put in cx, you get cx, so that works. Can you give me another example from R to R?
T of x equals x plus some other number.
Now let's try that.
Wait, but then now.
Suppose I put in 2x, would it work? What's it supposed to be though? You're supposed to be able to put in x and then put the t outside.
Okay.
Does that work?
X plus 0.
Thanks. What else could you do besides adding something?
T of x is 0, just said.
You could take the 0 function, that would work. T of x equals 0 for all x, that works. Something more interesting.
What if you scale
So,
like cx?
well, let's not use c, but let's say t of x equals 5x. Does that work?
Yeah.
So if I take t of x plus y, I get 5x plus y, which is 5x plus 5y, which is what it's supposed to be, t of x plus t of y. And if I take t of cx, I get 5 times cx, which is the same as c times 5x, because multiplication by real numbers is something or other. Commutative and associative, both, yeah. Okay. What about this one? Absolute value of x. What goes wrong?
If
Multiply by scalar negative.
Okay. Scalars,
A negative scalar.
negative scalars mess up. Addition, as Nick points out, will also mess up. So that doesn't work. All right. Well, that was not really that interesting, but the warning is, back in 9th and 10th and 11th grade, you were told that f of x equals mx plus b was a linear function. Not anymore. You can't have that plus b anymore. It's got to be linear. So the use of the language linear function that you had in high school, and maybe even in calculus here, is, I'm not going to say it's wrong, but it is no longer pertinent. Some evil politician got a hold of it. All right. Can anybody give me a linear map from Rn to R, where n is more interestingly bigger than 1? I'm saying that so Philip won't pull what he pulled on me yesterday. So like R2, can you give me a linear function?
You do t of x, y equals x. So that's
The magnitude of
Okay, so t of vector x, so you're actually just saying take a component, right?
yeah, take the first component.
So Bryce is saying take the first component of the vector x. Does that work? If you add two vectors and take the first component, is that the same as taking the first components and adding?
Yeah.
You scale the vector and then take the first component. Yeah, that works. Anyone else give me another example?
Can you explain that again?
Sure. So you're taking t of the vector x1, x2 here, say, and just taking x1. So if you added two vectors, so remember, Russell, how we actually add vectors. You add component by component. So this is t of x1 plus y1, x2 plus y2. And then the rule is take the first component, which is the sum of t of x and t of y. You okay?
And that's going from R2 to R.
To R1, right. When I wrote R here, I meant R1, yeah.
You can dot x with another vector, which is basically what you're doing there.
But more generally, for any vector A, consider the dot product of A with x. Comment?
Yeah, so in the first one, you're just doing the dot product of what we called earlier E1.
Good. Yeah, so you guys are right on it. So this example is the example of this with A equaling the first standard basis vector, E1, 1, 0, 0, 0. All right, so the properties of dot product tell you that this is linear, right? Dotting a vector with a sum is the sum of the dot products, and dotting a vector with a scalar multiple, the scalar pulls out. So I used those yesterday and said how important those were, right? So recall A dot x plus y is A dot x plus A dot y, and A dot cx is C A dot x. So question is, can anybody come up with a linear function from Rn to R that isn't of this form? Somebody said magnitude x.
Yeah.
Who was that?
I don't think it works under addition.
And it doesn't work under scalar multiplication again, just for the same reason that doesn't. Yeah, so magnitude x isn't going to work. So keep on the back burner the question of whether there are any besides these. Can anybody think of some geometric examples, say from R2 to R2? So what, if I think of vectors in the plane, what can I do to them to get other vectors in the plane that will behave in this fashion? What do you mean by, well, but I need a formula, t of x, tell me what to do to x.
cosine of theta, negative sine of theta, sine of theta, cosine of theta.
Okay, you're ahead of me. We're getting to that one later. So I haven't said what a matrix is yet, so you don't get to do that to me yet.
Rotate, reflect.
So one thing you might do is take a vector and reflect it across the x-axis. Think of we're going to do this a lot as we go on all year. Think of the x-axis as or the first axis as a mirror. You have an object here, and its virtual image is on the other side of the mirror behind the same amount. Remember that stuff from high school physics? Or from college physics? You did that today, all right. So what's a formula for this? T of x is what? So if I took x1, x2 here,
Negative.
You want negative.
X1, negative x2.
so the first coordinate stays the same, and the second coordinate, it becomes negative. Does that look linear to you? I'm not going to write it all out, but can you sort of in your head do this to x and y and do x1 plus y1, x2 plus y2? And then you'll see that it does in fact work. So reflection is an example of linear math. Various people also said we could try rotation. You could take the plane, and you could take vectors, and you could rotate them through some angle.
If it was like negative x to x1, that'd be a 90-degree rotation.
Okay, so hang on. So you're saying take x, and what'd you say, Taylor?
Negative x to x1.
So if I take the negative of this quantity and put it there, and I take this quantity and put it there, that seems to be the geometry that we talked about the second day of class, where you take this triangle and you flip it up over here, and that makes a 90-degree angle. Does that look linear to you guys?
Looks like a reflection.
Doesn't look like a reflection. Actually,
It could be.
because you've switched these two, so you've done two reflections. Wonderful theorem, by the way. Any rotation of a plane is a composition of two reflections. I invite you to prove that geometrically. I heard that. We see formulas here, and you can check from the formulas. By the way, this is a pattern we're going to continue through the whole year. We really should be writing t of vector x with brackets around it, but that's just too much stuff to write. It gets ridiculous to put brackets, parentheses and brackets. So with your permission, I'm going to do what the book does and leave out the inner brackets and just say t of x1, x2. That means t of the vector x1, x2. Be my guest if you want to waste all the ink of writing extra brackets in there. I'm fine with that. So you can check again from this formula that the rules work. Can you see geometrically why rotation should be linear? What if I took an x and I took a y, and then I took x plus y?
You just rotate it too.
What happens if I do t to this picture?
You just rotate that.
Well, now forget the algebra. If I rotate x and I rotate y, what happens to the vector x plus y? it rotates the same amount. What happens? You literally take this parallelogram and you rotate it. So where x plus y goes is the rotation of where x goes plus the rotation of where y goes. And stretching x and then rotating, clearly it's going to be rotate and then stretch. So geometrically, you should believe that this is linear. I'm not going to ask you to write out such arguments, but you should see that. So we can talk about linear maps and we can draw pictures, but in the end, you're going to want some algebra for computing with them. So those of you who have secretly in high school or college seen something called matrices might suspect that they have something to do with this. I guess I'll fix this. So, to a linear map from Rn to Rm, we will associate what's called an M by N matrix. So this will confuse you guys for a while. Notice the order of the letters.
Is that N?
This is M, and this is N. They switched orders, just to confuse you. Called the standard matrix of T. And I'm going to tell you how you do it. So this seems very mysterious, but you will see in 5 minutes that it's absolutely natural and you're going to be very happy with it. So here's the rule, and I'm going to then show you examples. So what is a matrix anyway? A matrix is an array, of numbers where you have m rows and n columns. So for example, I could put in, I could do a 2 by 3 matrix, and I could put in something like this. That would be a 2 by 3 matrix. Somehow or other, this is supposed to be telling you a function that maps which to which? R3 to R2. So you're going to input vectors with 3 coordinates, and it's going to output vectors with 2 coordinates. And here's the rule for how you make a matrix. And then I'm going to show you what you do. So you're supposed to have how many columns here? I'm supposed to have n columns. Well, n, that's the domain. So I'm going to have 1 column for each dimension I have in Rn. So what did we learn about yesterday? We learned about the standard basis vectors. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. I'm going to take T of the first standard basis vector. It's going to be a vector with m coordinates. I'm going to put it in that vector in here. So this is T of E1 is the first column. The second column is T of E2. I keep on going. The last column is T of En. So I just mechanically say, what does t do to the basis vectors? And I put those in as columns in order. That now has a matrix of numbers in it. So let's do that for our examples here. So let's do the reflection one. So first we had reflection across the x-axis, across the first axis. This guy. So you say to yourself, you're well trained. Here's E1. Where does it reflect to? When you reflect it across the first axis, where does it go? Stays where it is. So what's the first column going to be? So I started with 1, 0, and it stays where it is. It's 1, 0. That's the first column. E2. 0, 1 now. Where does it reflect to?
0, negative.
0, negative 1. It goes down here. That means the second column of my matrix is 0, negative 1. Okay, what about our 90-degree rotation matrix? Okay, so again, I draw the picture. Where does E1 go? So we're going to do stuff like this with 3 dimensions. I'll bring in toys on Friday, so we'll do some more stuff with this on Friday. Here's E1. Where does it rotate to? 0, 1. It rotates to there. So the first column is 0, 1. Where does E2 rotate to?
Negative 1, 0.
Negative 1, 0. So somehow or other, magically, these are the matrices that are supposed to be encoding, do these geometric things. Well, so there's got to be a step missing here of how we use this matrix A that we've constructed here to figure out what the linear map does to an arbitrary vector x. I've told you what it does to the standard basis vectors. Those are what these columns are. But now I want to know, knowing t of E1 to t of En, how do we find t of a general vector x? Question mark. You going to give it away?
Well, I know there's, okay, fine. It's x times the a, like using matrix multiplication.
Close. Not quite right, but close.
Oh, the other way around? A times x.
So let's just follow our noses and use the rules. How can I write x? This is what we did yesterday when you guys thought I was being silly.
Oh, x1.
x1 E1 plus x2 E2 and so on. Remember, the whole point of the standard basis vectors, these E's, is that you can write any vector as a linear combination of them. What does linearity say? I'm supposed to take t of this sum. Well, what's t of a sum?
The sum of the t's.
The sum of the t's. The sum of the things it does to each term. So by linearity, this is t of x1 E1 plus t of x2 E2 plus up to t of xn En. So we've used, oh, I erased it, of course. We're using the first rule for linearity. What does the second rule tell me?
With the constant.
Scalars can pull out. So this should be x1 times t of E1 plus x2 times t of E2 up to xn times t to the en. So the rule is, if you know these guys, they tell you that all you do is put in the x's as coefficients and you be done. Well, where do I have the information of what these things are? They're the columns of the matrix. So what I'm going to do is say that if I want to take this matrix, if I want to do t of x, I want to take x1 times the first column plus x2 times the second column plus xn times the last column. So here I have my matrix. So let me just do the example we have. If the matrix is the one we wrote down for the rotation, I want to take x1 times the first column plus x2 times the second column. If I want to rotate 90 degrees, that's this guy. So this is what Matthias was saying earlier when he was squelched. What do I want to do? I want to write down the matrix. I want to write down x. And I want to say, here's how we're going to multiply a matrix times a vector. So I'm telling you what this means. Matrix times vector means take this many of the first column plus this many of the second column. That's the rule for how you multiply. Don't ask why. Well, I told you why. The reason we want to make this definition is so that multiplying the matrix for the linear map times the vector x is computing t of x. So the definition is precisely made up so that you are correctly computing the linear map applied to the vector because of this rule. Now, some of you were sitting here saying, I've been taught how to multiply matrices before and this wasn't it. How many of you were saying that quietly? Really? How many of you have seen matrices before? And you're not sitting there saying that? All right, so let's do this with actual numbers. So I'm going to write down a matrix. Oh, okay, well let's first of all, before I do that, let's do this and check that it works with the formula. So the formula if I do this gives me what? How many in the first slot?
-8.
And how many in the second slot? So that is the formula we had over here for the rotation. So first of all, you should believe that that's consistent with what we figured out from the picture. Okay, let's do another example. Let's take 2, 3, -1, 7, 4, 5, and let's multiply it by the vector. How many things do I need here? I need as many as I have columns. So let's take 2, -3, 1. Okay, so now the definition I've given you is take 2 of these plus -3 of the second column plus 1 of the third column. Now, all you people who didn't raise your hands a few minutes ago, is this how you've done it before? No. Come on, I want to hear more no's.
No. Sir. No, sir.
Could you make that face one more time for the camera? Do you mind?
So, what have I got? I've got 4, 6 plus 3, negative 21 plus 4, 5. What does that equal? 4 plus 3 plus 4. This is the hard part.
Yes.
6, oh no, negative numbers. 6 plus 5 is 11, minus 21, negative 10. All right, so all you people, how would you have done this before?
I don't remember.
Matthias?
You would take the first row of the first matrix
Oh, yeah.
and multiply it by, like, multiply 1 to 1, so like 2 to 2, and then negative 1 to negative
When you
3.
say multiply, what are you actually doing?
Just taking the
You're
components.
doing dot product.
Yeah.
If this were on its side, you'd be dotting this vector 2, negative 1, 4 with the vector 2, negative 3, 1. You'd be taking 2 times 2 plus negative 1 times negative 3 plus 4 times 1. Well, is that what I actually did here?
Yeah.
Yeah.
It is what I did. But I did it in a conceptually very different way. Right? And then the second row, if you dotted that with this, you'd be doing this computation. And you'd be getting that answer. So why did I define it the way I did? Just to confuse you.
Yeah.
No, I did it because I wanted linearity to be built into understanding how when you multiply this matrix times x, you're taking the components of x times the columns, and that's the right computation. But the alternative understanding is so you can compute a times x, so this is what I just told you how to do here, a times x, using either linear combinations of columns, that was our definition, or dot products with the rows. So I will actually write notation for this. Maybe I'll do it now. So this always confuses people, but eventually you just get used to it. I can think of the matrix A as being made up either of n column vectors, which I will write with little letters, vector signs, and I will often put little lines like this to remind you that those are going up and down. Or, in which case, by the way, AX, we just said, is defined by taking the linear combination of the columns according to the coefficients of x. That's how we defined it. Or, you can think of A in terms of row vectors, and the row vectors will be capital letters going across. And how many of them are there? M. And then AX is the vector whose coordinates are the dot products of x with those rows. And as our guest videoer will testify, or will attest, there are going to be times where you really want to think about problems this way, and there are times when you want to think about problems this way. And the way they interact gives you a lot of very interesting stuff coming up. So for example, saying A times X is the 0 vector says what in these two setups? If you say A times X is 0, you're saying that an appropriate linear combination of the, which are the blanks of my matrix, columns. So an appropriate linear combination of the columns gives you, what's the second way saying? X is orthogonal to all the rows of A. Totally different conceptual framework, right? Saying that X is orthogonal to the rows of A is somehow telling you that X can be used to give linear combination of the columns that gives you 0. What? Well, I mean, it has to be right because you've seen right in front of your very eyes that the arithmetic comes out right. But it's very surprising that we have those two completely different viewpoints. All right, so I've told you how to multiply a matrix times a vector. And by the way, web work is open again this afternoon, and you will have computations to do for practice. So if you've never done matrix stuff, get in there and do it for practice. If you've done it, it'll be a little boring, but make sure you know what you're doing. There might be a few things I haven't gotten to yet that you need to look at the book for if you're going to start it this afternoon, but go ahead and do that. All right, so I've told you how to multiply a matrix times a vector. Suppose you had a matrix, A, and you had a vector with n coordinates here so that it would make sense to multiply. But suppose I had several of those vectors. What would be a natural thing to do?
Take from each one.
You could do the sum, but you could just do the computation column by column, could you not?
Yeah.
You could make the answer as a collection of columns where for each column here, you would get an answer column there.
Oh, that's really interesting.
Guess what? That's how you multiply matrices. So if this is a matrix B that happens to be n by something or other, what will be the shape of the answer? Well, it has as many rows as A has, and it has as many columns as B has. So for example, let's actually cheat. Let's use the same A I had before. And I'll use the same first vector I had before. And then let's say I have a second vector. What should the answer be? What shape? Two rows, two columns. Do you know what the first column of the answer is going to be?
11, negative 10.
How'd you do that so fast?
Oh, they call me a wizard.
11, negative 10. Do the second. Say what?
312.
312. How are you doing so fast?
So I didn't want
They
to
call it
answer that one.
Look, if you just say I want none of these plus one of these plus one of these, you can do it in your head like faster than Mallory did it. You can just say this plus this plus this. Easy. Or you could do it the long way. So by the way, most people do this with two hands and go like this.
I'm not that coordinated.
The very first time I was in graduate school and I had to teach linear algebra, I had messed up my back and I couldn't move this arm. That made it very difficult to teach this stuff. I actually had to get one of the students to be a guest gesturer. guess that line didn't go over so. Question.
Something was wrong with it, but I can't put my finger on it, so.
The question is, we started with a matrix A that was 2 by 3. We multiplied it by a matrix that was 3 by 2, and we got an answer, not surprisingly, that was 2 by 2. So the thing to ponder while you're pondering, A, we said, represents a linear map from whom to whom?
2 to 3. 3 to 2.
3 to 2.
Yeah.
B represents a linear map from
2 to 3.
2 to 3. No.
Yeah. Yeah.
Why not 2 to 3?
Yes. That,
Yeah.
So does M by N.
Yeah.
Yeah.
How could you do R to 3 to R to 2 to R to 3?
Right, something's wrong here.
2 to 3.
Doesn't make any.
Ah, okay. This one represents a function from,
2 to 3.
what do you think? So A corresponds to a T, B corresponds to an S. What do you think multiplying A times B does?
And R2, or no, R3 thing.
No?
No,
S
R2.
and P, nice.
So the beauty of all this is that multiplying here should mean that you do this, which means you should be doing a composition of functions where first you do B, and then you do A, and you do the composed function, which is written with my initials perfectly done, T composed with S, other things which you won't say, and this matrix represents the composition of functions. So matrix multiplication is made up so that it exactly mirrors composition of functions. So I will start with that tomorrow and show you why that really is true. We're going to do a bunch more examples